Okay, differential equations, 7.4. Take a look at some review up here up at the top. Let's just say, hypothetically, a Laplace transform of a function f of t is some other function, capital F of s. And in other words, that's really what we have, just writing it backwards right here. What we're seeing is, what if, just like before, guys, what if instead of just doing a transform of f of t, what if now we wanted to throw in another function multiplied to f of t? In other words, it's t to an n power. Now, by the way, I'm going to scroll to this over here. We already dealt with that in an earlier section where we said, hey, remember this transform where if we had e to the at times little f of t, you might remember that we had a way of dealing with that issue if e to the at was multiplied to our transform. Now, instead of having an e to an at multiplied to our function, what if we have t raised to a power? You'd say, well, what would happen? What happens, guys, is this right-hand side. The exponent n becomes very, very, very important in this problem. You want to know what this transform is? It's -1 to the n, and it's going to be the nth derivative of capital F of s with respect to s. The nth derivative. So with no further ado, let's take a look at this. Looking at the problem from this regard, let's just say that if I gave you a Laplace transform of t to the 1 of e to the 3t, you could see that our n here would be 1. You'd say, well, wait a minute, what's your f of t? Well, by the way, your f of t would be e to the 3t. And here's some more review. What do you think the Laplace transform of e to the 3t was? You guys remember that? 1 over s minus 3. And you might say, where are you getting that from? Look at the top of the screen. Remember we said, look, if you had e to the at, you might remember right when we were starting off, we'd always get 1 over s minus a, right? You'd say, well, that's what I've got right here. You'd say, well, good. But now, this was just a little bit of review. We're going to say, well, if n's equal to 1, look what we have in green. We're going to say it's -1 to the 1, and I'm going to take my first derivative of 1 over s minus 3. I'm going to have my Laplace transform, but I'm going to have to take my first derivative of 1 over s minus 3. Now, as we do that, first off, I hope you would agree that we'd have -1 to the 1 is simply -1. And by the way, this is really like s minus 3 to the -1. So how do I take the derivative of that, guys? Bring down a -1, and then what do we get? S minus 3 to the -2, right? You know, that's s minus 3 to the -1. We're just using that power rule. Say, what is that transform? Unbelievably, it's 1 times s minus 3 to the -2, which is 1 over s minus 3 quantity squared. So that's how we can go ahead and get this transform if I have t to a power multiplied to a function. Really, it's not so bad. Let's take a look at our next one. You could say, well, guess what your n is here? Once again, n is 1. You'd say, no, wait a minute, what function am I dealing with? You're dealing with the Laplace transform of sine of 5t. Here's your f of t, isn't it? You've got your t to a power multiplied to another function. What's the Laplace transform of sine of 5t? Do you guys remember? 5 over s squared plus 5 squared, which is really 25, right? Now, once again, let's look at the top here just for a second. We need to have -1 to the n, So we've got negative 1 to the 1. And then we're going to take our first derivative of 5 all over s squared plus 25. Okay? So at this point, I guess I just want to say again, negative 1 to the 1 is a negative 1. And maybe you even want to say, hey, wait a minute, isn't this really 5 and it's s squared plus 25 to the negative 1, and we'll take our derivative of that thing. We're going to need the chain rule, won't we? A derivative here, we bring down negative 1. Negative 1 times 5 is negative 5. We'll have s squared plus 25 to the negative 2. What's the derivative of the inside? 2s. So what exactly is this transform? Well, a negative 1 times a negative 5 is a positive 5. 5 times 2s is a 10s. And then don't forget this other thing's going to come down. We'll have s squared plus 25 whole thing squared. We doing okay? Yeah.
Just like a general question, if you have us like on the final, would you ever put like a t to the fifth or a t to the fourth, like the coefficient?
Yeah, it's probably not going. I'm not going to be asking you to take super high power derivatives, because honestly, that's not what I'm really trying to test. I think even right here, as you're seeing this next example, this is going to be more work than our last one for sure. Taking consecutive derivatives here, you can say, now wait a minute, n equals 2. Yeah, and we're going to have our Laplace transform of sine of 4t. And what's that? Help me out. What do we get? 4 all over s squared plus 16. You got it. Now here you can see life is going to get messier. It really is. We're going to get negative 1 to the nth power. That's negative 1 to the 2. But now look at this. We're going to take a second derivative of this thing right here. Now, stating the obvious, the first derivative won't be so bad, right? The first derivative, I think, will be pretty easy, I hope. It's the second derivative where I think you're going to see we're going to be forced to use a quotient rule. And that's okay. Look, negative 1 squared, you're just going to have a positive 1. And you can even write this. You could say, well, I'm going to take my derivative of this thing, which, by the way, here it's 4s squared plus 16 to the negative 1. What is that derivative with a chain rule? What do we get? Negative 4, then what? S squared plus 16 to the negative 2 times a 2s. And here's where life gets a little ugly uglier. And you might say, why are you writing ds out there? Well, here's my first derivative, and then I'm going to take another derivative after that, right? So I'm going to have to take the derivative of, let's see, it looks like I'll have a negative 8s all over s squared plus 16 squared. And this is where, let's be honest, it's not going to be the prettiest problem. But we can still do it. We can definitely still do it. You could use a product rule. I'm going to use the quotient rule, though. We'll have low. Here's s squared plus 16 squared. D high, what's the derivative of our high function? Negative 8, right? Minus high. D low, now I got to take my derivative of the bottom. What's that? 2 s squared plus 16 to the first. Chain rule, what else is going to come out? A 2s. And then down below we'll say, oh my gosh, now I'm going to square that denominator. I'll get s squared plus 16. Square a square and you now have a fourth power. And right now that can get a little bit intimidating as you look at this. But I do want to tell you this much. If you're thinking about factoring, that's a good thing. Look, both of these have s squared plus 16 up here, and I can pull something out. Both of these actually have a negative 8s, or negative 8, pardon me. So tell you what I'm going to factor out from this top. I'm going to say, look, I'm going to pull out a negative 8, and I'm only able to pull out s squared plus 16 to the first power. I have that second component, that second part of the numerator. I only have one of those that I can pull out. But then what's left? Well, this negative 8 was gone, and one of these factors of s squared plus 16 are gone. I'm just going to have one of them left. When I'm looking all around here, a negative 8 is gone, so I'm going to be left with a plus. I do have an s left. I do have a 2 left and a 25. 2 times 25 is 50, and I'm going to have a 50s. It's just a 50s, and right there, you can see we're practically done. We've got our s squared plus 16 to the fourth. If you want to clean this up a little bit, you can cancel one of those factors up on high. You can say, well, I've got s squared plus 50s plus 16. And then down below, I just have s squared plus 16 to the third. Okay? So, yeah. Did I drop a negative? Well, I lost this negative right here, so all this first part is going to be positive, right? Okay, sorry guys. This was a negative 8s. We had a copy mistake. By the way, this is 2s, not a 25. So when we factor out this negative, as we're going to be gone here, you can see what's going to happen. We are still going to have a minus here, aren't we? We're still going to have a minus, but 2 times 2s is going to get you a 4s squared, right? It's going to be a 4s squared. Sorry about that. Mistook an s for a 5. That's one of the dangers of using this. And then a 1s squared minus 4s squared is a negative 3s squared plus your 16, right? And I think we're good now. Okay? Sorry about that. Okay, as we continue, as we go to the back, you can see that originally we had a transform for e to the at. And we said that that would become capital F of s minus a. But today we learned this new form. Sometimes you could do a problem either way. And that's what we're about to do right now. So we've got method 1 right here. Let's go back to our first transform. And we're going to say, hey, let's bring the e to the 3t out in front. This is how you did the problem when you first got into this a while back. So a would be 3. And what we're seeing is we could just do the transform on t. We'd say, hey, just do this transform on t, but s is going to move to s minus a. We're going to move that to s minus 3. So you might remember that's what we were doing before. Now, what is the transform of t to the first? What would we get? 1 over s squared. But we're going to say, wait a minute, that's going to get shifted. Wherever you have an s, it's going to become s minus 3. Final answer will be 1 over s minus 3 squared. Okay? And our video is about to end.